So we're going to look at an organic chemistry test in the subject of organic chemistry, and this comes from DAT Bootcamp. So let's get right to it with question number 1. We're looking for an intermediate in the bromination of toluene. So just to review this mechanistically, if we consider toluene, which is methylbenzene, it is one of the pi bonds in the aromatic ring that acts as the nucleophile. And we're going to have bromine, a bromine atom that's actually complexed with the Lewis acid. And so mechanistically, we're going to find that we are going to make a carbon-bromine bond. The bromine-bromine bond is going to break. We're going to get a series of complexes that we call sigma complexes. And I'm going to show all of them. What's important to remember with these sigma complexes is that we're going to have a series of resonance stabilized carbocation intermediates. And these carbocation intermediates will occur ortho and para to where the bromine has been added. So I'm showing the bromine being added to the para position. I could just as easily show it being added to either of the two ortho positions. And I'm doing this on purpose so that it matches up with one of the answer choices. This carbocation in particular is really stable because not only is it allylic, but it's also tertiary. And of course, you could have one other sigma complex. And one thing you should notice is the location of these positive charges relative to the bromine atom that has been attached to this molecule. Ortho to the bromine, para, and I should say it's the carbon that's bonded to the bromine, ortho to the carbon that's bonded to the bromine. This is the one that's especially stable in energy. So let's take a look at our answer choices once again. We do not make a bromonium ion intermediate. That's incorrect. This looks like the second sigma complex resonance contributor that I drew. The problem with this is that you do have a carbon-hydrogen bond that is made. So C is incorrect. D is incorrect because it's not a meta-director. And E is incorrect because it's not a carbanion equivalent. So B is certainly the best answer. So we're going to go ahead and pick B and move on to the next question. Which of the following reactions represents a propagation step in free radical bromination? Remember, propagation means you have a radical that's a reactant and a radical that's a product. So if we look at A, this is an initiation step because the radical is a product only. If we look at B, it's a termination step because radicals are reactants only. If we look at C, I have a radical as a reactant, radical as a product. That's my answer. I'm done. Number 3, if you're going to look at elimination, you've got to be able to draw the Newman projection, show that the leaving group and the hydrogen that is removed in the mechanism are anti to one another, and then predict your product. So this one's going to take a little bit of effort. So let's go to the easel for this. Before I do that, however, let's just look at answer choices that we can eliminate. This is an elimination reaction, so you can absolutely get rid of D and E. Secondly, if we look at answer choice B is not feasible because I've scrambled the skeleton of the molecule. I know I'm going to lose this H, I'm going to lose this Br, I'm going to have a double bond. The question is, will the phenols be cis or will the phenols be trans? The only two possibilities in this question are A and C, and you cannot easily tell by looking at this sawhorse projection. You must look at the Newman projection. But do not ever pick D or E because they're not elimination products, and you can't pick B because you scrambled the carbon skeleton. E2 does not rearrange. It is a concerted reaction, much the same way an SN2 is a concerted substitution reaction. So this being said, let's go to the easel. And what we're going to need to do is I need to draw this Newman projection. And what I'm going to do with the Newman projection is I am going to look down the bond of this CC bond. So my mind's eye is going to be on this carbon that bears the bromine. Remember, the little dot is the carbon that I'm looking at. And if I rotate this, the bromine is going to be straight up. And the methyl group will be down and to the left, while the phenyl group will be down and to the right. And on the back carbon, the hydrogen will be up and to the left. And the phenyl group will be up and to the right. And in the same plane will be the methyl group. What I'm going to do is I'm going to hold the front carbon steady, and I'm going to rotate the back carbon 120 degrees counterclockwise. So when I do this, rather than redrawing this, I'm just going to erase the groups on the back and redraw them. Now the hydrogen is anti-periplanar to the bromine. The phenyl group will be up and to the left, while the methyl group will be up and to the right. Now in the mechanism, when I have my strong base, we remove the hydrogen atom. The double bond we're going to make is going to be in this plane, so it's really hard to draw it, but the electrons are going to be kicked into the plane, and the bromine is the leaving group. What I'm left with is a carbon-carbon double bond where the phenyl groups are anti one to another, as are the methyl groups. That is a trans double bond, and so I was only considering A and C, and now A is the best answer. C would be a cis double bond, A is a trans double bond. But you must draw the Newman projection before you can see that. Question number 4. Which of the following statements best describes the stereochemistry at the reactive site of an SN2 reaction? I am not very pleased with the answer choices because SN2 is not stereospecific. Stereospecific means that there's only one stereochemical result. There is net inversion of configuration, but not complete net inversion of configuration. And so I like B the best. If we look at A, we don't have retention of configuration, or we certainly don't have net retention of configuration. If we look at C, we don't get a racemic mixture, that's SN1. If we look at D, we don't get a racemic mixture of products because that wouldn't be stereoselective. If we look at E, that's just straight up bullshit any way you slice it because that's amenable to, there's no way of predicting that. B is the best answer that remains, but it is not stereospecific, it is stereoselective. Regardless of all that, we're going to pick B and move on to number 5. Major product. Now, this is something that we've discussed recently. The substrate changes only very slightly. But to quickly discuss this, you would have a proton transfer, then a rearrangement, and then bromine's going to attack the more substituted carbocation. That means answer choice A is the credited response. And we've already podcasted a couple of videos that talk about that mechanism. The initial carbocation would be on the second carbon, but you get a hydride shift that puts the carbocation on the carbon that's bonded both to the phenyl group and the methyl group, and then bromide attacks that carbon, which is consistent with answer choice A. Number 6. How many signals will be present in the proton NMR spectrum of the following molecule? Well, you have hydrogens here, and here, and here, and here, and here. These two methyl groups are chemically equivalent, but they're distinct from this one because of their proximity to the carbonyl carbon. So these would represent one environment. Both of these hydrogens would represent a second environment, and these methyl hydrogens would represent a third environment. And there's a fourth one that's bonded right here. In the terse structure, we don't show this hydrogen, but there's a hydrogen right here, which would be a fourth environment, so we're going to pick D as our answer choice. So if we review just a little bit of theory about thin layer chromatography, there is a competition between a mobile phase and an immobile phase. So let me give you just a few notes on chromatography. So TLC, or thin layer chromatography, there is a competition between two phases. Now, the physical property that is the basis of TLC is polarity. So there are two phases. One is called the mobile phase, and the mobile phase is going to be the solvent that we use. And the immobile phase is actually the silicon dioxide that's in silica. Now, this is a covalent network, so this is very polar. While the solvent that we use relative to the immobile phase is relatively nonpolar. And so polar molecules will stick to the silicon dioxide and not move very far. The measurement that we use to quantitate movement is the RF value. Non-polar compounds have very large RF values, while polar compounds have very small RF values. So if we go back to the question, which one has the highest RF, they're asking us which molecule is the least polar. That certainly is going to be the straight up alkane. Pentane would be our answer for number 7. Number 8, all molecules are capable of hydrogen bonding except one. I don't like this question either, because implicit in this is hydrogen bonding with each other. That's not what they're asking. They're asking either as a donor or as an acceptor. All of these molecules can engage in hydrogen bonding except for one, and that one is going to be D. So this would be an acceptor, a donor or an acceptor, neither. Because you have to have a highly electronegative element with a hydrogen attached, or a highly electronegative atom with a lone pair. And by highly electronegative atom, we're talking fluorine, oxygen, or nitrogen. Molecule D has none of those properties. How many carbon signals? This one's a really symmetrical molecule, so this carbon and this carbon are equivalent. This carbon and this carbon are equivalent. These two carbons are equivalent. That's 3 environments. Answer choice D is the best one. Following compounds have similar molecular weights. Which would be isolated first in distillation? Certainly nothing that can significantly hydrogen bond, so let's get rid of B and D. And the more branched it is, the less accessible surface area is available to engage in van der Waals forces, so E is the best one. E would be the lowest, then C, then A, then D, then B. When we're looking at conformations, we know that the most stable conformation has the biggest, bulkiest group as far apart as possible. That would be the 2 methyl groups. Again, recall this methyl group is on the front carbon, the one that I'm looking at, and this methyl group is on the back carbon, the one that I can't see. And so the most stable would be staggered and anti, while the least stable would be eclipsed. And really, we don't use the term syn in Newman projection, so those really don't fit at all. E is the best answer for number 11. Which the following is a meso compound? E and C look very tempting, but they're not chiral, because this has 2 methyl groups, this has 2 methyl groups. So we can eliminate those. D isn't chiral either. B has 2 chiral centers and no internal symmetry plane, so it's not a meso. That leaves A as the meso. 2 chiral centers, but an internal plane of symmetry such that the left half is the mirror image of the right half. Number 13, if it's an enantiomer, every chiral center needs to be inverted. So we can stop. A can be eliminated because these 2 carbons have the same configuration. These can be eliminated because B has this carbon, the same configuration. If you look at C, however, inverted, 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 there's our answer. Number 14, functional groups. You have to be careful here. This looks real tempting to call this an ether, but it's actually what is called a lactone, which is a cyclic ester. So I only see ester on one answer choice, and ester and an alcohol. That's correct. And then just move on to the next. IUPAC for the following molecule. We have 1, 2, 3, 4, 5, 6, 7, 8 carbons, so we can get rid of B, and we can get rid of D. We can also get rid of E because we don't name things as a T-butyl group. So this literally leaves A and C as possible answer choices. And so what's the difference between those two? Alphabetical order is the difference between those two. This is not an alphabetical order. This is, I'm going to choose C. This is a typical Grignard reaction where we react an ester with a very powerful carbon nucleophile. So the intermediate would be a ketone, which will react with another equivalent to give a tertiary alcohol. We see a tertiary alcohol in A, not in B, not in C, not in D, not in E. That's an easy choice. A is the best answer. Major product of the following aldol condensation. Here we need to be careful because we know that the nucleophile will be this molecule. There's no alpha hydrogen here. And so A and B are good answer choices. C would not be. D would not be because they don't have an alpha proton. And E would not be. Now we just start looking at conformation. The phenyl ring in close proximity to this T-butyl group is probably one of the worst ideas since Napoleon decided to start a land war in Asia. So let's go with B. Number 18, I'm going to reduce this to an alcohol, and then I'm going to replace the OH with a BR. E is definitely the best choice on that one. So it doesn't do any chemistry to the aromatic ring. This becomes a CH2OH, and then finally a CH2Br. And the only answer choice that's consistent with that is answer choice E. What's the major product of the final reactions? Well, this is going to be base catalyzed opening of an epoxide. So the attack is going to be at the less substituted carbon. And secondly, you'll protonate to make an OH. So A looks good. B undergoes inversion. That's not correct. This substitution isn't correct. Neither in D, neither in E. We're going to go with A. So you need to have confidence in the products of these reactions and know what you're looking for and quickly discard what is not consistent with that. So you don't start considering everything. So very quickly, I see the substitution pattern doesn't work for C, D, or E, and that the stereochemistry doesn't work for B. So I'm going to pick A, and then I'm going to move on to the next question. What we'll do here is we'll remove the alpha proton, and then it will attack acetone, and we'll get an alcohol. So A looks really good. I'm still going to have the triple bond, so get rid of B, get rid of C, get rid of D, get rid of E. Again, the distracting answers that they're putting on this test aren't very close, so that makes them easier to answer. Number 21, we have an ester, but the carbonyl, a carbon that has a partial positive charge, is bonded directly to the benzene ring. That means it's going to be a meta director, and we're going to add a chlorine. Not meta, not meta, meta, done. Which of the following reagents will accomplish the following transformation? This is a trans double bond, so I want the radical reaction with sodium and ammonia. If I wanted the cis double bond, I would use H2 and Lindlar's catalyst. This is a Diels-Alder reaction. We conserve the stereochemistry, so it has to be cis. I'll have a 6-membered ring with a double bond. Best answer is going to be A because this shows the endo effect while the others do not. And by the way, I would be really surprised if you saw this on your DAT. I need osmium tetroxide to convert a double bond to a syn-diol, and I see that for D. 25, lowest pKa. First of all, the carboxylic acid is stronger than the alcohol, so let's get rid of C, let's get rid of E. Secondly, strong electron withdrawing groups are better. There's none here, there's 1 fluorine here, there are 2 fluorines here. 2 is better than 1 is better than 0. 26, 2 Bronste-Lowry bases. Look at what becomes protonated. So the amine becomes protonated, OH minus becomes protonated, therefore it must be D. 27, least acidic. Selenium is bigger than sulfur, is bigger than oxygen. So this would be the most acidic, then this would be next. OH with a fluorine would be more acidic than OH with nothing. OH with nitro would be more acidic than OH with nothing. Let's pick OH with nothing. Which Lewis structure, reasonable resonance? What will happen is I can push, and then I can push, and then I can push a lone pair. So we'll look for that conjugated array. It looks like the conjugated array is on choice B. Too many electrons, carbon making 5 bonds, just classic errors, and those are the things you want to look out for. 29, hybridization, sp2, sp, sp2, that's E. And finally, all are aromatic except one. This one's not aromatic because it doesn't have 6 pi bonds.